Hello, my name is Jaden Finney, and this is Physics Lab 3, Magnetic Field of a Bar Magnet. Alright, so the purpose of this lab is to analyze the induced magnetic field of a bar magnet with a magnetometer. Magnetometer. Bar magnets have a north pole and a south pole, with the magnetic field traveling from the north end to the south end, similar to a dipole. In this report, we will find the relationship between distance and the magnetic magnitude of the magnetic field. Alright, so for our models, the magnetic field of a bar magnet could be expressed based on whether it's on or off axis for the observation position. The Biot subart large states that the magnetic field is due to the current and the distance between 2 points. And I have 4 formulas here of the magnetic field dipole perpendicular to the position axis, as well as a natural log form finding k and n, n's the slope, and l and k is the intercept of the graph. I also have the magnitude of the magnetic field of a bar as well. So assumption, so we're going to assume that both poles of the bar magnets are symmetrical, creating an even magnetic field, like no damage, no altercation, nothing like that. It should be symmetrical. And the system is going to be our magnetometer, and the surroundings are everything else, including the bar magnet. Alright, so for the experiment, first we downloaded magnetometer apps to find where on our phone is the magnet. Then a meter stick was used to locate where the magnetometer was on the phone. Then we found 5 distances where the magnetic field equaled 20, 70, 120, 170, and 220 microteslas, respectively. And then using the natural log formula, in the last couple slides, we found that our slope of the line was negative 2.97, and the y-intercept, or LMK, was negative 14.78. We use these values to find U, which is the magnetic dipole moment, where U we found to be 3.37. And then here is a graph of how I calculated using some Excel stuff, basically using the off-axis field, and right there we have the line as well as the formula for it. And yeah, it's actually a negative slope, which is good, which means seems that we have an inverse proportional relationship. And right here is my glow scope code for everything. I calculated, and these were for ideal conditions for the computational data, like no influence from a bunch of outside stuff and everything. I calculated the position vectors, the magnitudes of position vectors, our perp, and as well as the magnetic field perpendicular to the axis, given those formulas. And yeah. So for our results, a trend shows that there exists an inversely proportional relationship between distance and magnetic field. As distance increases, the magnetic field decreases, and vice versa. The magnetic field increased by about 0.0006 teslas from the furthest positions, and our two B fields, experimental and computational, from our glow scope data was actually quite different from each other. The experimental B field was actually much larger in magnitude compared to our computation data, and there's actually no Z component with the computational B field. So 2 what ifs is what if I didn't orient my experiment to compensate for magnetic north. The B field would be different from the experiment since it would not take account for Earth's natural magnetic B field or magnetic field. And if I stuck 2 identical bar magnets together and reran the experiment, what would happen? Generally, the B field would actually double, as the magnetic dipoles from each bar magnet are actually pointing the same direction and not opposite. So you should get double of the magnetic field that you found previously. Cool. So in short, there is an inversely proportional relationship between the distance vector r and the magnitude of the magnetic field. The magnitude of the magnetic field is also greater with the experimental data compared to the computational data, which is actually very interesting. This can be most likely caused by several sources of error, I believe, including the influence of unaccounted fields from outside devices, like even my laptop, for example, distance measurements, and the stability and legitimacy of the magnetometer app, because it was free. I don't know how accurate it would really be. Using a more controlled lab environment would result in like experimental data that aligns closer to the glow script data. That is my video, and thank you for watching.